live session. In today's session, we are going to discuss about the units of storage in computer system. As you know, computer systems stores the digits and the alphabets that we type through the keyboard in bits and bytes. That is a computer's language of storing everything and accessing everything. Also, they interpret everything or perform operations on all numbers using bits and bytes form only. So in today's video, we are going to talk about the same. Also, we'll take a look at what ASCII values refer to, and we'll see a few questions along the way as well. So let's begin the session. Let me share my screen with you guys. Alright, so today's session we are going to start by understanding bits and bytes. Now let's first understand bits. A bit is the smallest unit of storage in a computer system. Okay? So everything in a computer system is built around this bit system. It can only have two values, 0 or 1. A bit at a time can hold just two values. Either it can be 0 or it can be 1. It is the building block for data storage in computers. So since bit is the smallest unit of storage, we further come to bytes, kilobytes, megabytes, terabytes, and we talk about computer storage in reference to all of this. Now let's move on to bytes. 1 byte is a grouping of 8 bits, also known as octet. So let's say we have 1, 2, 3, 4, 8 bits. 0, 1, 1, 0, 1. Alright. So this set of 8 bits is what we call as a byte, also known as octet. Now 1 byte can be used to store one letter or character, A, X or any symbol at the rate, exclamation marks. 1 byte can hold these symbols. So moving on, let's see a question. How many distinct patterns can be made with n bits? So you have n bits, how many distinct patterns can you make with them? Let's see. With 1 bit, you can make 2 distinct patterns, since a bit can store only 2 values, 0 and 1. With 2 bits, you can make 4 distinct patterns as shown, 00, 01, 10 and 11. With 3 bits, you can make 8 distinct patterns, 000, 001, 010, 011, 100, 101, 110 and 111. So these are the different patterns that you can make using 3 bits. Now moving on, as you can see, we have observed a pattern here. We add 1 bit and we double the number of combinations. So in 1 bit there were 2 combinations, in 2 bit there are 4 combinations, and in 3 bit there are 8 combinations. So every time a bit increases, the number of combination gets doubled. Now mathematically, n bits yield 2 to the power n patterns. Alright. So if there is 1 bit, the number of patterns is 2 to the power 1. That is 2. Now if there are 2 bits, the patterns are 2 to the power 2. That is 4. Alright. Now when we move on, we talk about ASCII representations. Let me check the sound quality so that you all hear it.
Please repeat it.
Is the voice clear now? Let me explain this question again. How many distinct patterns can be made with n bits. So if you have 1 bit, distinct patterns are 0 and 1. If you have 2 bit, distinct patterns are 0 0, 0 1, 1 0, 1 1. If you have 3 bits, there are 8 distinct patterns. Alright? So if we see what the pattern is, we can find out that every time we add 1 bit, we are doubling our number of combinations. As you can see, when we have 1 bit, our combinations are 2. Now we increase the bit by 1, our combinations get multiplied by 2. So if you try to convert this pattern to a mathematical equation, it can be said that n bits yield 2 to the power n patterns. Now this formula is going to be of very use while writing certain examinations, because there are many questions that are formulated around this formula. Let's see one such question. And first, let's take a look at ASCII representations. How to store numbers and digits in computer? To answer this problem is where we have ASCII representation introduced. So ASCII stands for American Standard Code for Information Interchange. Computers can only understand numbers. So an ASCII code is the numerical representation of a character. So suppose you are storing A. So the numerical representation of that character has to be found out to store it in computers. 1 byte is used to represent a character or number. And 1 byte can hold a number between 0 to 255. So since 1 byte has 8 bits, and we saw that 8 bits can give 2 to the power 8 distinct patterns. So that means 8 bits can give us 256 distinct patterns. Now in these 256 distinct patterns, if we assign each pattern to a number, we can get numbers between 0 to 255. Alright? Now, in ASCII representation, these 0 to 255 characters or these 256 combinations that we obtain are assigned to different characters, like A to Z is represented by the numbers from 65 to 90. Small a to Z is represented by numbers from 97 to 122. Similarly, our numbers 0 to 9 are represented by 48 to 57. And the remaining numbers that we have left in the range from 0 to 255 are used to represent special characters or symbols on the keyboard. So let's see quickly a question. An 8-bit unsigned integer has the following range: A 0 to 255, B 128 to 127, C 255 to 254, and D 0 to 509. So we are talking about an 8-bit unsigned integer. What do you think is the answer for this question? So 8-bit means 2 to the power k different combinations, that is 2 to the power 8 different combinations. So by 2 to the power 8 different combinations, and if we see for unsigned integers, that's correct. We'll see 0 to 255 different combinations. Alright. Now moving on, how do we store integers? An integer is a number with no fractional part. So when we say we are talking about an integer, we mean that we are not calculating the 0.5, 0.25 or the fractional part of the number. Alright. It can either be positive or negative or 0. A computer system uses bits to store every information. So numbers are also stored in bits in the computer system. And integers can be divided into signed and unsigned integers. Now, in a single decimal digit, you can write a number between 0 to 9, correct? If you get 2 decimal digits, you can represent numbers between 0 to 99. Similarly, we have a pattern here. 9 is equivalent to 10 minus 1. 99 is equivalent to 10 to the power 2 minus 1. Now 2 here is the number of digits. That is 99 has 2 digits. So we have done 10 to the power 2 minus 1. So therefore, in n decimal digits, you can write a number between 0 to 10 to the power n minus 1. Now an unsigned integer containing n bits can have a value between 0 and 2 to the power n minus 1. So remember, we are talking about unsigned integers. We are not considering negative numbers as of now. So an unsigned integer can be represented with n bits from 0 to 2 to the power n minus 1, which gives you 2n different values. Now let's quickly see a question around the last formula that we saw. So there is a new data type which can take as values natural numbers between and including 0 and 25. Alright. So we have a new data type that takes values between 0 and 25. How many minimum bits are required to store this data type? Okay, Pooja says 4 and Murli says 5. Keep in mind the formula that we talked about, correct? N bits, 2 to the power n minus 1. So using n bits, you can represent numbers from 0 to 2 to the power n minus 1. So to represent 0 to 25 numbers, what would be the value of n? So the answer is 5. There can be certain manipulations of questions around the same formula, but this formula is mostly asked in written examinations. Let's take a look at another question. A 10-bit unsigned integer has the following range: 0 to 1000, 0 to 1024, 1 to 1025 or 0 to 1023. Again, keep in mind when reading these questions that whether they are talking about signed integers or unsigned integers. Since we have just talked about unsigned integers, this question is in reference to unsigned integers. And then move on to check how many bits are we talking about. So the number of bits is 10. And the formula is again the same that we discussed before. 0 to 2 to the power n minus 1. So in place of n, simply put 10 and calculate how or what the last value would be. So these options that you see here are fairly confusing because 24, 25, 23 are all talking around the same vicinity. So your calculation needs to be perfect. So 2 to the power 10. 2 to the power 10 gives you 1024. Now minus 1 gives you 1023. So the correct answer here is D, 0 to 1023. If you would have been asked how many different combinations can be made, then the answer would have been 1024, 2 to the power k. Alright. Since we are talking from 0, we subtract 1. So remember the formula, 2 to the power k minus 1. So k bits represent numbers from 0 to 2 to the power k minus 1. Alright. So when you do that, 2 to the power 10 is 1024, minus 1 comes out to be 1023. Moving on, let's now talk about signed integers. We have seen how unsigned integers are stored. Now again, since we have negative numbers, we need some way to store that also in our computer system. In our everyday life, we use a simple symbol of minus dash sign in front of the number to say that now it has become a negative number. But computers don't work like that. They have to understand in the form of bit patterns whether the number is negative or not. Alright? So, there are different ways to do the representation of signed integers that has evolved over the years. So, one way came in the picture, then we saw that there are certain difficulties in representing negative numbers with this particular way. So, we moved on and evolved to the next way to represent the numbers, and so on and so forth. So, today we will discuss three such ways. First one is signed magnitude method of negative number representation. Setting the most significant bit to 0 or 1. So for example, you were representing numbers with 8 bits. Now you will represent numbers with only 7 bits. And the leftmost 8th bit you will use to represent whether the number is negative or positive. How? Let's see. 0 is used when the number is positive and 1 is used when the number is negative. So if the leftmost digit of the bit pattern is 0, that means your number is positive, else the number is negative. The remaining bits in the number, as I said, the remaining 7 bits will indicate the absolute value of the number. So for example, I have shown you two examples here. One where the leftmost digit is 0, that is decimal representation of 10, and one where the leftmost digit is 1. So that becomes the decimal representation of minus 10. So instead of using the minus symbol that we use in our everyday life, we are using the bit 1 to say that this number is negative. Alright. So let me quickly show you what problem we had with this representation system. Now if you add 10 and minus 10 in real life, the answer is 0. Correct? So mathematically, if you are adding 10 and minus 10 or 5 and minus 5, answer should come out to be 0. But by this representation system, if you add 10 and minus 10, the answer doesn't come out to be 0, it comes out to be minus 20. So I hope you know the addition. 0, 0 gives 0. 1 and 1 when you add, it gives 0 and a carry of 1. Then again 0 and 1 will come out to be 1. 1 and 1 will give you 0 with a carry of 1, and so on. So the final number that you got here is minus 20, which is totally incorrect. So the computer should be able to do these mathematical calculations correctly. To keep that in mind, we came out with the concept of 1's complement. What is 1's complement? To get 1's complement of a number, all you have to do is reverse the digits or the bits of the number. So this question also can be asked in certain written examinations. They can give you a pattern saying that this is a number, find the 1's complement of this number, or find the 2's complement of this number. Alright, so 1's complement, okay, what do you want me to repeat, Pooja? 1's complement? See, binary arithmetic problem was that we have decimal 10 and we have decimal minus 10. Alright, now if we add this decimal 10 and minus 10, let me show you. So 0 and 0 come out to be 0, 1 and 1 come out to be 0 and with a carry of 1. So with this carry of 1, you again get 1 here. Again 1 and 1 will give you 0 and a carry of 1. This 1 will come down here. 0, 0 and 0 and 1 will add up to 1. So this number should ideally have been mathematically 0, right? But this number came out to be minus 20. So this is the problem with our signed magnitude representation, and that is the reason why we moved on to 1's complement. So what does 1's complement do? How you get 1's complement is, let's say if you have these bits 0, 0, 1, 1, 0, 0, 1, alright, and you have been asked to find the 1's complement of this number. All you have to do is you have to reverse these digits. For example, wherever you see 0, you place 1, and wherever you see 1, you place 0. So the ones complement of this number would be 1, 1, 0, 0, 1, 1, 0. Alright, fairly simple. So let's move on to the topic here. 1 plus 1 plus 1. Okay Ram, let me show you. So 1 plus 1 plus 1 if you have to check. Alright, first you do 1 plus 1 gives you a carry of 1, and then you add 0 with 1. So that output should be 1, 1. Alright. Now moving on. Decimal 10 is represented as shown on the screen, correct? Its one complement would be reversed digits. So all you have to do is you have to reverse these digits. 1, 1, 1, 1, 0, 1, 0, 1. Okay? So this number that we have obtained by reversing the digits comes out to be 245. Since we are using 8 bits, the maximum number represented is 255, right? When we use 8 bits, the maximum number you can represent is 255. The minimum number is 0, correct? So the complement of a number is the largest number represented with the number of bits available minus the number itself. Okay, so as we see here, this is the representation of decimal 10. Now we reverse the digits. So this is 1's complement of decimal 10, which is 245. Now the maximum number is 255. So 255 minus 245 gives you your minus 10, or ideally say 245 minus 255 gives you minus 10, which is your negative number. You'll understand this more in the next slide where I'll show you an example. So this number, the binary number, represents bit representation, gives you decimal 3. Now what we are trying to do here is we are adding decimal 3 with decimal minus 2 to check if this representation solves our problem of arithmetic addition. Alright. So what we have to do next is simply do addition. So when we do addition, we get 256. Now I hope you understood the addition concept. Alright. 0 and 0 when you add, that comes out to be 0. 1 and 0 you add, that comes out to be 1. 0 and 1 is again 1. And 1 plus 1 is 0 and a carry of 1. Alright. These are the simple mathematical rules of bit addition in computers. So whenever you are adding like 3 minus 2, or if there is any other question of the sort, add these two numbers, add these two binary numbers, or add these two bits, keep in mind this mathematical formula and then go ahead to solve your problem. So in this 3 minus 2 addition, you can see that we have used all our 8 bits and there is a 1 carry left out. Okay. So in situation like this, when there is 1 carry left out, we move this carry at the end again and do the addition again. So now we have removed this 1 from here and we will do this addition, and that will come out to this, which is decimal of 1. Understood? So replace the leftmost 1, which is the extra bit, since our number is represented by only 8 bits. Represent this leftmost 1 with the carry into the first bit. Okay? I hope you are able to see the video, guys. So I'm moving on to 2's complement. Now 2's complement calculation is also fairly simple. Add 1 to the 1's complement of a number and have its 2's complements. So let me say an example for you. Decimal 12 is represented by these 8 bits: 0, 0, 0, 0, 1, 1, 0, 0. Alright. So if you have to find the 2's complement of decimal 12, first you will convert this into 1's complement. So you will reverse all the bits and get the 1's complement. So you have got the 1's complement. Now what you do is you simply add decimal 1 to the 1's complement. And when you do that addition, the value you get is 2's complement of 12. Now since 1's complement also had the issue of taking the leftmost bit, adding it again to your solution to find the right solution, we moved on to find 2's complement representation of bits. So in 2's complement, we take the number, find the 1's complement, add 1 to the 1's complement, and finally get the 2's complement of the number. Alright. So let me quickly show you now the addition process using this. So we have decimal 12 and we are adding decimal minus 5 to it, and we have to get the correct solution. Alright. So let's see. 0 and 1, 1, again 1, 1, 1 and 1 will give you 0 with a carry of 1, 0 and 1 and 1 again 0 with a carry of 1. So similarly you will get 0 and there will be finally a 1 carry left out like it was in 1's complement. But this time, since we are working on 2's complement, we got to know that in 2's complement we don't at all have to worry about the carry. So if there is a carry, if there is not a carry, you don't need to bother about it. Whatever 8 bits you have got are the final solution, and they are, as you can see, the correct solution. So if you convert these bits into the number, you will find that they are representing decimal number 7. Okay. Let's move on and quickly see a question. A data type is stored as 6-bit unsigned. Okay, focus on the question unsigned. Alright. Don't hurry up through these questions because sometimes you misinterpret signed with unsigned, and in the tension of the moment you just mess your answer when you know the concepts. So a data type is stored as a 6-bit unsigned integer. Which of the following cannot be represented by this data type? So you have 6-bit unsigned integer. So unsigned integer will represent negative as well as positive. Okay. So again, use the same formula: 6-bit 2 to the power 6 minus 1. And when you do that, you will get to know which number cannot be represented by 6-bit unsigned integer. Right, 32. Moving on, a new language has 15 possible characters. Alright. So there is a language which has 15 possible characters. This question is from a previous AMCAT paper. So you might get questions around there is a new language, these many characters are there, how many bits will be used to represent this sort of questions. Okay. So let's see. A new language has 15 possible characters, 8 different punctuation marks. So there are 8 punctuation marks and a blank character. If you have to create 2 data types, first one to store the letters of the language. So by letters we mean 15 plus 8 plus 1 blank character. Alright. So when we are talking about letters, they are talking about 15 plus 8 punctuation marks plus 1 character. So these many letters. Okay. To store the letters of the language, and second to store any character. So for second only 15. How many bits will be required to store these 2 data types? Keep in mind there is just one plain simple formula to do these questions. So 1, you have to find out how many bits will represent this and how many bits will represent 15. So let's see, 2 to the power 2 minus 1. What does it give you? 3. In 3 you cannot do anything, right? 2 to the power 3 minus 1. What does it give you? 7. Again you cannot do much with it. 2 to the power 4 minus 1. This gives you 15, right? So you can see that with 4 bits you can represent 15 characters. So the answer for the characters part is 4. That means you have possible 2 choices, 3 and 4 or 5 and 4. Now moving on to figure out how many bits can represent all the letters. So like I did for this, similarly do for this. By all letters we mean 15 plus 8 plus 1. So this is 24. So 2 to the power 5 minus 1 if you do, you will be able to represent these 24 characters. So your answer is C, 5 and 4. Okay. So as you saw, these bits and bytes questions are fairly simple to understand and there isn't much logic involved. There is a very simple formula that you have to keep in mind and you have to understand how we got that derivation of that formula. Also, right now we discussed ASCII characters, alright, ASCII representation. Mulli, what do you want? Okay, let me repeat this last question for Mulli. A language has 15 possible characters, 8 different punctuation marks and a blank character, 1 blank character. So, how many total characters are there in the language? Mulli? Yeah, number of total characters in the language came out to be 24, okay? If you have to create 2 data types, first one to store the letters of the language, by which we mean all letters, 24 letters, and second to store any character in language. So there are characters 15. So we need one data type to store 24 different things and another data type to just store 15 different characters. Now they are simply asking how many bits will be required to store these 2 data types. Okay, as we have seen that k bits can store 2 to the power k different patterns, 2 to the power k different combinations. So all you have to do is simply figure out 2 to the power k is equals to 24. So with what power of 2 can give you 24 or more than 24, or what power of 2 will give you a number 15 or more than 15. So as we saw, 2 to the power 4 gives us 16. So we can use 16 different characters using 4. So this part is solved. So 4 is the correct answer for characters. Now we have to decide for all the numbers. So since 4 was used for 15, we tried out 5 for 24. So 2 to the power 5 will give us more patterns than 24. So C came out to be the answer. Alright. Now as I was saying, we discussed ASCII pattern and ASCII way of representation. Alright. But that representation method might soon be outdated and Unicode might take over. Now if you have heard about Unicode representation can take many more characters than ASCII. Okay? How? ASCII representation uses 8 bits while Unicode uses 4 bytes to store different characters. So imagine the number of characters that can be stored. So all the Chinese characters, all the Italian, Japanese or different characters, that language characters that you want to store can be stored using Unicode representations. While ASCII representation is very limited since it is using 8 bits and it has 256 different combinations only. So there is a very limited number of your regular keyboard letters that you can type and you can store. While we are not using Unicode right now in our regular processing, or why you're not getting Unicode questions instead of ASCII in your written exams, is because using Unicode for regular mathematical day-to-day operations or work becomes way too expensive. So all we need is 8 bytes to represent our numbers, alphabets, special characters, right? So if we use 4 bytes of Unicode, all that space goes to waste. That is the reason why we are still currently sticking in majority of computer systems with ASCII representations. You can go back and Google on ASCII and Unicode differences and find out some interesting facts about the same. Now before we close this session, I would want to give you a very interesting question that we saw today that I think you should be able to answer. Okay? So let's see. There is a for loop. This is a C question. There is a for loop. For I equals to 0, okay, I less than equal to int max. So I hope you know what int max is. If you don't, you can very well go back and check what int max does in C++. This is a very basic loop, okay? I is equals to 0, I less than equal to int max. Now inside this loop, what I am doing is printf I. Fairly simple. %d/n, comma I. Okay? And we just close the loop. Very simple piece of code. I hope you can all see it. For I is equals to 0, I less than equal to int max, I plus plus, printf %d/n I. So you have to print the value of I till the loop runs. So what I want you to do is, I want you to figure out how many times will this loop run and what all values of I will be printed. Okay? We'll take this question up in our next session. Keep practicing, guys, and happy coding. Hi everyone, welcome to this session on frequently asked OOPS questions in AMCAT exams. In AMCAT exams, OOPS questions form a major part of the programming section. Out of the 25 questions, 6 to 7 questions would generally be from OOPS. And these are very moderate level questions, not very intricate questions that you would have to spend more time on. So if you have grasp on general topics like polymorphism, abstraction, objects, classes, basics of OOPS, it's very easy and quick to get through all these 5-6 questions and be sure that you'll score these questions.
Hello everyone, welcome to this free live session which is on trees and graphs. As we have seen in earlier videos also about trees and graphs, today in this session we are going to take some questions which are coming from trees and graphs most frequently in various tests, mostly in AMCAT, and we will try to solve it. And there are many other different types of variations on the variations of questions that are framed on trees and graphs, but we are looking into the type of question which is generally difficult for a student to answer, and we will try to solve them, and we will see a few other types of questions that are framed on these topics in the sessions later.